Howdy. So today I'm going to be deriving an equation that gives us the optimum angle to launch a projectile if you want to maximize range when there's a height difference. So as many of you probably already know, when there's no height difference and you're just launching on level ground, the best angle if you want to optimize range is going to be 45 degrees. And so preferably we're looking for an expression that will work whether we have a positive height difference or a negative height difference. So with a positive height difference, it's going to be slightly higher than 45 degrees. And with one that's negative height difference, it's going to be under 45 degrees. But in either way, we want to maximize this range, which we're going to call x. So we're just going to set up our equations for projectile motion. In the x direction, we get x is equal to cosine theta v naught t, because it's just constant velocity. And in the y direction, we have constant acceleration. And at the end of the projectile's trajectory, the y coordinate is going to be the height difference. So we're going to get h is equal to, and since we were only worried about height difference, this is the launching point is the origin in the y direction, so there's no y naught, and that's going to be equal to sine theta v naught t minus g over 2t squared. All right, so if we want an expression for the total range in terms of the height difference, we're going to need to eliminate the variable for time. So we're going to use a quadratic formula on the second one and plug it into the first. I've tried it the other way, and I haven't been able to consistently get the equation we get at the end. And the algebra and trig for this method is, I wouldn't say a lot cleaner because it's still pretty messy, but cleaner. So we're going to move everything to the h side, and we're going to get g over 2t squared minus sine theta v naught t plus h is equal to 0. So if we're solving for this, we just use the quadratic formula. We get negative b, so that's going to be sine theta v naught plus minus square root of sine squared theta v naught squared minus 4 times g over 2, so we'll just call that 2g, and h all over 2a, which is going to be just g. So these are our times. Now this plus minus is going to get a little bit annoying, but if we look at our diagram here, we know that in this projectile's trajectory, it'll reach the height difference at 2 points in its trajectory. The first is going to be over here, and the second is going to be over here. So we're just worried about the second solution, because we want to maximize how far it gets in the x direction by that point. And it's the same thing with the negative height difference. If starting at time equals 0, it only has one solution, but if you were to continue the projectile going backwards, you'd have a negative solution where it would be at the same height. But in either case, we want this positive answer because we want this to be the greater of the two solutions. And since the square root isn't defined for real numbers with negatives, we can count on this always being positive. So we're going to be adding a positive number to make this, or to give us the greater of the two solutions with respect to time. So we can just get rid of the negative. So this is what we get for time: sine theta v naught plus square root of sine squared theta v naught squared minus 2gh over g. And we're going to plug this back into our expression for x, which is the range at that point in time. So at the end of the trajectory, we want to know how far it's gone in the x direction. So we get x is equal to cosine theta v naught times sine theta v naught plus sine squared theta v naught squared minus 2gh under square root and all over g, which we're just going to multiply to the other side. because we're going to end up taking a derivative of this. And so if we get as many constants to this side as possible, we end up with we don't have to worry about them, because when we take the derivative and we set it equal to 0, the constants won't matter. So in this term, I'm going to bring a v0 out from under the radical by dividing everything under the radical by v0 squared. And so we're going to get sine theta. I should factor it all out. So we get v0 squared cosine theta, because we have the first v0 and we're taking out the second one from in here and in the radical, plus square root of sine squared theta minus 2gh over v0 squared. Now this should look kind of familiar, because so this is basically like multiplying the potential energy, dividing it by the kinetic energy. So if this would be the same as writing gh over 1/2 v0 squared, which is kind of interesting, and I guess that shouldn't be too surprising, because the optimal angle is going to be related to how much potential energy, or how much kinetic energy you're giving up for potential energy in order to meet the height difference requirement. So yeah, we get g of x, or gx is equal to cosine theta v0 squared times all this. So we'll divide both sides by a v0 squared, and we'll distribute the cosine. So we get gx over v0 squared is equal to sine theta cosine theta plus cosine theta square root of sine squared theta minus 2gh over v0 squared. So now we're going to take the derivative of this, so we're going to get gx prime over v0 squared is going to be equal to, now we have product rule here, so we have derivative of the first term times the second term plus the derivative of the second term times the first term. So derivative of sine is going to be cosine times cosine is going to be cosine squared, plus sine times the derivative of cosine, which is negative sine, so that's going to turn into a minus sine squared theta. And we do the same thing here, where we'll do the derivative of cosine first, negative sine theta times square root of sine squared theta minus 2gh over v0 squared, all just square root, and it's going to be plus cosine theta times the derivative of this, which we'll just use the chain rule for, so we're going to get 1 over 2 square root sine squared theta v0 squared minus 2g, sine squared theta minus 2gh over v0 squared, and multiply by the derivative of the inside, which we have sine theta squared, the 2 sine theta times the derivative, which will be cosine theta, so we're going to get 2 sine theta cosine theta. These 2's cancel out, and this is the derivative of just this radical. So we multiply that by cosine, and we're going to get cosine squared sine theta over square root of sine squared theta minus 2gh over v0 squared. So we're going to set this equal to 0, and we're going to move cosine squared minus sine to the side where our x prime was. So we're going to get sine squared theta minus cosine squared theta is going to be equal to, actually, we're going to move the other two terms to that side. Probably doesn't matter too much, but so we're going to get cosine squared theta minus sine squared theta is going to be equal to sine theta square root of sine squared theta minus 2gh over v0 squared plus, or no, sorry, minus cosine squared theta sine theta over square root of sine squared theta minus 2gh over v naught squared. So looking if there's a common term between all of them, and there isn't, unfortunately. So to get rid of these radicals, we're going to end up squaring both sides, which gets pretty messy. So we're going to have, if you remember FOIL, we're going to get the first term squared, cosine to the 4th power theta, minus 2 of first term times the second term, minus 2 sine squared theta, cosine squared theta, and plus the second term squared, plus sine to the 4th theta is going to be equal to first term squared. We're going to get sine squared theta, and then the radical will go away. Theta times sine squared theta minus 2gh over v naught squared, minus 2 times these two terms multiplied by each other, so the radicals will cancel each other out, and we're going to get minus 2 sine squared theta, cosine squared theta, and last we have the second term squared, which is probably the ugliest to deal with later, and we get minus, we know it's plus, because we square it, cosine to the 4th theta, sine squared theta, so we're just squaring the numerator and the denominator, over sine squared theta minus 2gh over v naught squared. So, oh, there should have been a 2 here, because we have it once when we FOIL it from the one side and the second from the other one. And if you notice that these two are the same on both sides, so they just cancel. And what we're left with is cosine to the 4th theta plus sine to the 4th theta. It's going to be equal to sine squared theta times sine squared theta minus 2gh over v naught squared, plus cosine to the 4th theta sine squared theta over sine squared theta minus 2gh over v naught squared. Okay. So let's see if we can get rid of these sine squareds. We're going to continue on the next page. So I'll just rewrite what we had at the bottom of the previous one. So we get cosine to the 4th theta plus sine to the 4th theta going to be equal to sine squared theta minus 2gh over v naught squared plus cosine to the 4th theta sine squared theta over sine squared theta minus 2gh over v naught squared. Okay, so we can rewrite cosine in terms of sine, because if you remember from sine squared plus cosine squared is equal to 1, we can write cosine squared as 1 minus sine squared. That's going to be equal to cosine squared. And cosine to the 4th is just cosine squared squared. So if we multiply this by cosine squared, we should get sine squared theta minus sine squared theta cosine squared theta plus sine to the 4th theta going to be equal to sine squared theta sine squared theta minus 2gh over v naught squared plus cosine to the 4th theta sine squared theta over sine squared theta minus 2gh over v naught squared. So this cosine squared we're just going to write as 1 minus sine squared. And then we're going to divide every term by a sine squared. So we're going to get cosecant squared theta minus 1 minus cosine squared theta plus sine squared theta is going to be equal to sine squared theta minus 2gh over v naught squared plus cosine to the fourth theta over sine squared theta minus 2gh over v naught squared. So we have a sine squared on both sides here, so we can just cancel those. And if we bring this to the other, well, if we factor out a negative out of here, we get negative 1 plus cosine squared. That actually doesn't do anything for us, so let's try moving. So at this point, actually, let's take a slightly different approach here. So we have sine squared theta and a sine squared theta on this side. Let's move this cosine squared theta over here, and we'll get sine squared plus cosine squared theta, which will be just a 1. And if we move this 1 over to the same side as this 1, we're going to get cosecant squared theta plus sine squared theta going to be equal to 2 minus 2gh over v naught squared plus cosine to the fourth theta over sine squared theta minus 2gh over v naught squared. So does that make sense what we did earlier? So we had a sine squared on both sides, and we had a cosine squared on this side. We moved the cosine squared to this side, so we had sine squared plus cosine squared, we got a 1. We moved this 1 to the other side, we got a 2, and we left the sine squared how it was. So now looking at this, we're just going to multiply every term by this denominator here, which will be but so we get cosecant squared times sine squared is going to be equal to 1 minus 2gh over v naught squared cosecant squared theta. We'll take the next term, we get plus sine to the fourth theta minus 2gh over v naught squared sine squared theta. And on the other side, we get, is equal to 2 sine squared theta minus 4gh over v naught squared. And then we get minus 2gh over v naught squared sine squared theta plus 4g squared h squared over v naught to the fourth power plus cosine to the fourth power on this side. So looking at both sides, we got a negative 2gh over v naught squared sine squared on both sides. Those will cancel. Whoops. We have a sine to the fourth on one side and a cosine to the fourth on the other side. So I think we should be able to rewrite that into something that will cancel. So we get sine squared theta minus sine squared theta cosine squared theta. And on this side, we get a cosine squared theta minus sine squared theta cosine squared theta. And these two will cancel out. And we're going to get 1 minus 2gh over v naught squared cosecant squared theta plus sine squared theta is going to be equal to cosine squared theta plus 2 sine squared theta minus 4gh over v naught squared plus 4g squared h squared over v naught to the 4th power. Okay, so if we subtract the sine squared from both sides, that goes away, and this 2 sine squared just goes to sine squared. And if we look here, we get, whoa, sine squared plus cosine squared theta. That goes to a 1, and that cancels with just 1 on the other side. And so we're left with negative 2gh over v naught squared cosecant squared theta is going to be equal to negative 4gh over v naught squared plus 4g squared h squared over v naught to the 4th power. And now we're going to multiply both sides by a negative v naught squared over 2gh. So on this side, we just get cosecant squared theta, and then it's going to be equal to, so the v naughts will cancel, the negatives will cancel, and we just get 2 and minus 2gh over v naught squared. And this is where we get our expression from. So we know that the critical points of the angles sorry, I should say that the range as a function of what your initial angle is, the critical points of that function will be described by this expression, and we're just going to clean it up a bit. We'll take the square root of both sides, so we get cosecant theta is going to be equal to square root of 2 minus 2gh over v naught squared. And then we'll take the inverse of both sides, so 1 over cosecant theta is going to be sine theta is going to be equal to 1 over square root of 2 minus 2gh over v naught squared. And then we're going to take arc sine of both sides, and so we're going to get theta optimal is going to be equal to arc sine of 1 over square root of 2 minus 2gh over v naught squared. And I guess just to make see that it makes sense, if we plug in 0 for h, so on flat ground, we just get 1 over square root of 2, which is root 2 over 2, which is the sine of 45 degrees. Similarly, if the height difference was equivalent to the over infinity is greater than, or is a positive height difference, then it'll be the square root of 2 minus some, so the denominator will be getting smaller, which means that this will be getting bigger. So we're looking for a sign that's increasing, which will be a higher angle than 45. And similarly, if h is negative, this will become positive, making the denominator bigger, making the inverse smaller, so we're looking for a shallower angle, because sine increases from 0 to 90 degrees. So if you ever wanted to know what the optimal angle for launching a projectile is when there's a height difference, this equation gives you the answer. And I guess, you know, I'm just going to rewrite it so that it looks clearer. So theta optimal is just going to be equal to arc sine of 1 over square root of 2 minus 2gh over v naught squared. So, yeah.